let's look at the homework assignment. Semi-infinite wire that has two pieces, and we went over how to do those pieces in class. Is that one completed?
I think so.
Okay, so you can't actually look and see.
Yeah.
That's fine. Things to make sure you don't overlook are things like draw a sketch using a ruler, right? These want to treat it like, like you're doing an engineering project, very precise. And make sure you include all the things that it says. So you got pretty detailed stuff here on what it says to do. Then what ideas we'll be using in determining it. For this one here, you're using the idea of Coulomb's law.
Right. I think it's like Coulomb's law, and everything else is Gauss's law, right?
Well, there I think are a few other odds and ends, but
okay.
Yeah, you want to make sure you think about what idea it is. And here you're adding more stuff to the sketch. Then this here, what is the electric field magnitude and direction due to the infinitesimally small element identified in part 3? So you will have had on your diagram, you'll have, here's the wire, and I think this is the one where your point is up here, and then you should have there an arrow, DE, and some little piece down here that's DQ is equal to lambda DZ. Right? You should have those drawn. Now, obviously, I didn't draw what I just did with a ruler and whatnot. I'm just making sure you know what you need to have. So when it says, what is the electric field magnitude and direction due to the infinitesimally small, can be resolved to X and Y components, you should, show that on the picture. And then in words, you write, it's all in the positive Z direction because, it's away from positive charge. And then the last here, that's the place where math really comes into play. Actually, there's math here too, because here you're setting up what DE is. And here you're setting up the integral expression, so you're identifying your limits, and this is the X component, Y component, Z component. Of course, there's only one component for part A, two components for part B. And so the math is in those last 3 steps. So a lot of this is just idea stuff, making sure you understand the ideas.
Right.
And then you go through the same type of thing for the next one. The dipoles, you remember what I said about that?
Something about a common denominator.
Yes. You want to have a common denominator, and you don't have, your limit is as R is much, much greater than L. And so your limit is not going to be going to 0. You would have it going to 0 if you didn't do a common denominator. If you do the common denominator, you're getting something that's not 0, and it's showing the functional form of how it's moving as it gets larger. Now, charged non-conducting sphere. This one here is very much like the homework problem you've already done, right? The difference here is its rho is B square root of R. I think it was B times R in the homework problem that you had to do on the computer.
I think so too.
That we went over.
Yeah, and I still have that sheet.
So note your first thing is what's the total charge in the sphere. So that's the only place where true integration occurs in this problem, because you have to integrate, and this is going to be 0 to capital R because you're doing the entire sphere. Now, if you get down here, of course, you have draw your sketch, blah, 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 what ideas, drawing your Gaussian surface, what assumptions do you make? The assumptions is always a tough one. We are assuming that, and I say this is an assumption, based on symmetry, the electric field has to be radial. And so with my spherical surface, the electric field is parallel to D. Those are what I put in there for the assumptions. And they're more than assumptions because they're required by symmetry, but we're assuming symmetry.
Yes.
Calculate the electric field as a function of R. Now this is a function of R, so what's the difference in outside and inside? Inside, the amount of charge enclosed is going to differ depending on where you are. and that's what part B is inside. So it's you're gonna have to do this integral again, but going out to some r that's less than capital R.
Right.
And then finally, when you're outside, the charge enclosed is what you found in part A. You don't have to calculate it again. And so the outside part is the easiest. And then make sure you do this. Because I've had a lot of students who forget the plots. You had a plot up at the top as well, plotting the charge density up here. So there's two plots, one the charge density and one the electric field. Number 4, we're going to start in. I highlighted here before I started the things that are going to be what we're finishing up today. So we should be finishing up the rest of these in today's lecture. So now it's time to start the real lecture. Now, if you look at these slides, I included slides that we went through last class period. So we're going to go really quickly just as reminders until we get to the new stuff. Now, this picture is actually a sphere that we're going to talk about, but we're going to do cylindrical, well, a wire and things like that, just to make sure we can do that. So you remember doing this 2 weeks ago?
Yeah.
Using which law?
This one was Coulomb's.
That was Coulomb's law. Now we're going to redo it today using Gauss's law. So I have that there for us to remember. We were able to do it. We were able to get an answer. And the what we would find in this, and I think that I had my X and Y crossed or something. I don't remember. Remember we were talking about that last class period. But what we should have found here is that the X component is 0 and the Y component, if you go from minus pi over 2 to pi over 2, you just get 2 for this integral. And so it's 2 k, and q2 is actually we have to put in, well, we had to make a few changes because lambda is q2 over L.
Right.
But now we had Gauss's law, which is summarized. Where is it summarized? Yeah, summarized here. If you look at the net flux coming out of the surface, you can determine how much charge is enclosed. That's the summary. The mathematics of it, we have to know how to calculate the flux. So here's the calculation of the flux, integral, and it really looks better if you don't use the highlighter.
Yes.
That circle means we have a closed surface, no holes through it, of electric field dotted to dA. And this is the actual law. And so what's the difference in that and this? Well, this one here, I've put the definition of the flux, how you calculate it. So that's our actual law, and we use that law usually to find electric field, but we could use it to find charge enclosed as well. So here are the things to remember as you're solving the problems, which would be problems 3, most of the ones after 3. A question we had last time, and this is going to lead us, the next slide is the first non-review slide.
Right.
So what kind of symmetry did we have that was exploitable if we had a spherical charge distribution? Spherical. Why was it important to identify this? I'll give you the simple answer. So we don't have to do calculus.
That's right.
We made our arguments based on symmetry to make what was a calculus problem that could potentially be hard into something that was so easy we didn't have to do the calculus. So identify that if we have a point charge or charge on a sphere, that we're going to have spherical symmetry that we can exploit. So I know generally you're told not to be exploitative, but we want to exploit that symmetry to make our calculations easier. So now, sorry, these were repeats again.
Yes.
Here's the one that's the new.
Right.
What type of exploitable symmetry does an infinitely long straight wire have?
No.
It does have one.
Oh, then it would be planar, wouldn't it?
It's not planar. It must be cylindrical by process of elimination.
Yes.
So it has a cylindrical symmetry.
Why?
Now, if I have an infinite wire, notice the word infinitely.
Yes.
If it's an infinite wire, then the only parameter that's going to matter is how far you are from that wire. Your vertical elevation doesn't matter if it's a vertical wire. Your elevation doesn't matter because it's infinite.
Right.
So there's no change as you move up and down. And going around in a circle doesn't matter because it looks the same no matter how you are on that. So it has a cylindrical symmetry. And so based on that cylindrical symmetry, we need to choose a Gaussian surface that will exploit it. So what shape should I make my surface that I use for, remember the Gaussian surface is a theoretical surface that we use for calculation. It's not a physical thing. It's not like we put a cylinder somewhere.
Right.
And now that I've given you the answer,
It's a cylinder.
it's a cylinder. Good job.
I mean, if it's
Now, let me ask dumb questions just so you can answer something. I don't know if it's my hearing or it's my voice, but everything I say sounds weird right now. How does this work for you?
I mean, it kind of irks me, but it's still cylinder-ish.
It's cylinderish, but is it going to exploit our symmetry?
Oh no,
Where does it have to be located to exploit our cylinder?
it has to be in the wire, or the wire has to be in the cylinder.
So it has to be coaxial with the wire.
Right.
Coaxial means the center of the cylinder is the wire. Now, let's explore what we're doing with Gauss's law. Gauss's law, we're calculating flux, right?
Yes.
And so we have to calculate the flux over the entire closed surface. How many surfaces does a cylinder have?
3.
3. The top, the bottom, and the side. So we have 3 regions to calculate based on. Now, using our brains, if I have a wire and this wire has a net positive charge, okay, so I just made plus 5 microcoulombs per meter just so we have a number to think about. So we have a positive charge. What direction do electric fields point with regard to a positive charge?
Out.
Out. Based on this symmetry, what is that going to mean? Like if I were to take a little piece right here, what direction would the electric field from that piece point? All directions, right? But if I take an infinite wire, then for this piece here, there's going to be some other piece up above or some other piece below that will have the same horizontal or vertical components.
Right.
And so those are all going to add out to zeros. And my electric field has to be radial. Now, I drew it outward because if it was a positive charge per unit length, it would be outward. But it could be inward.
That makes sense.
But it has to be out radially with that cylindrical symmetry.
That makes sense.
So what is the angle between the dA on the side and the electric field?
90 degrees.
0. Close. What you mean is probably correct. Remember, okay, so here is my electric field, and dA is always pointing directly out of the surface. And so the angle between dA, which is directly out of the surface, and the electric field is 0. They're parallel.
Right.
You were probably thinking from the plane to the electric field instead of the normal to the plane, which is the direct.
From the electric field back to the wire.
Okay, that would also, yeah. But dA and E is what's important because remember, the flux is equal to integral, well, I'm taking off this circle because I'm just doing on the side. You might not be able to read that, but that says side.
Okay. Yeah.
That makes it much more readable.
Much more readable.
So I'm going to have the electric field vector dot dA, but on the side, E is parallel to dA. I'll put S for side here. So E dot dA is just equal to E times dA. So that's the first thing, exploiting the symmetry. Second thing, exploiting the symmetry, because I have this cylinder that is it's coaxial with the wire, then the electric field at a constant distance from the wire has to be constant in magnitude.
Yes.
It can't get stronger as I go around the circle because it's symmetrical.
Because it's equidistant from the outside of the cylinder is equidistant from the wire.
Yeah. And so we also have as a second rule, ES is constant on cylinder or on surface. So this becomes bring a constant outside of the integral, but by definition the integral of dA is just A. And the area of the side is, and now this one here you might not know offhand. The area of the side is actually easy to figure out if you think about, what if I take that cylinder, slice one side and flatten? Then I would have a rectangle, and the length would be the circumference, 2 pi r.
Right.
And the height would be the height of my cylinder. I didn't define a height for the cylinder, did I?
No.
So the cylinder has some randomly chosen radius r and height h. And so that's going to be ES times 2 pi RH. So that's the flux on the side. Are you with me? Because you have to do this in what, problem 4? Problem 4, I think, is the one with the coaxial cylinder. Well, coaxial cable. You're calculating the electric fields in coax cable. That's including the top and bottom.
Right. Yeah. Okay. So 2 pi r squared is the top and the bottom. Okay.
Yeah.
Yes. So that makes sense to me.
Okay. So we've done the flux on the side, but we have the top and the bottom to be concerned about.
Why? I thought you said they cancel each other out.
I didn't say that. Now, we're going to find that they're unimportant to our solution, but I did not say they cancel each other out.
Okay.
What direction is the area on the top? Remember, dA is normal to the surface.
So it's up.
So there's dA for the top.
Bottom, it's down.
There's dA for the bottom. What's the angle between dA and the electric field for the top?
That's going to be 90 degrees.
That's 90 degrees. How much is parallel for 90 degrees?
0.
So when we do the dot product, E dot dA is 0 for the top.
Some sense.
So the flux in the top is the integral of E top dot dA equals 0 because E top is perpendicular to dA.
Hold on. Why is the E top perpendicular to dA?
Because the E has to be pointing in the horizontal plane. And dA was vertical. Right, my E's that I drew before are still correct. Anywhere you are for this wire, they have to be pointing out radially.
And they can't be pointing up and down because it's small.
Because the wire is infinitely tall, so it makes no difference.
Charge and the up and down cancel each other out. Okay, so I guess
Okay, I'll let it percolate for a while. But if you have questions later on, like if you're working on this afternoon and you're like, well, this afternoon you'll be in the lab. But you know, if you have questions, you're like, wait, I don't understand it, come back to me. I want to make sure it is understood. Not just trust me, it's the way it is. So the flux on the top is 0, and likewise the flux on the bottom is 0. So it turns out this is the entire flux. Now, if we're going to use Gauss's law, here's where I actually gave the problem definition. So we'll continue on the next slide where I gave the problem definition, just continue from where we are. So what we have is the electric field on the side times 2 pi RH is equal to the charge enclosed over epsilon 0. Right-hand side I haven't done anything with yet.
Yeah, that's right, because the flux is equal to, okay, yes, I remember that.
So yeah, let me put the flux here just. But if we look at the picture, if I have charge lambda per unit length, or lambda is the charge per unit length, then how much charge is enclosed by my cylinder that is a height h?
That times h?
That's it.
Lambda times h?
That's it. So Q enclosed is equal to lambda h. So the h is in my flux, but I said the h can't matter. Now it's in my charge enclosed as well. All that's left is let's solve for the electric field.
Which is epsilon 0, right?
No, which is E.
Wait,
So
epsilon 0 is a constant?
yes, that's the permittivity of free space.
Okay.
So I just have to divide everything by 2 pi RH.
So the h's cancel out.
Which is a big relief. If the h didn't cancel out, you know you're wrong.
Okay. And then we're left with a bunch of things. Why did you separate it out like that?
Because I wanted it. I want us to see where this goes, and since lambda is charge over length.
How did you get from epsilon to that 2K or whatever?
That was our definition from. That's the definition of K. So 2K is 1 over 2 pi epsilon 0.
Got it.
And notice the last one, I replaced lambda with Q over L. Now if we go back to that opening slide, oh, there it is. This here, remember I said this is just going to give us 2 if we have an infinite wire. And this was 4, so we just cancel one of the charges to make it electric field. And so this gives us electric field in the y direction is equal to K Q over L Y, and then that's 2, so I have to have it multiplied by 2. And that is what we just found. That's the same equation as we just found, except for Y versus R, because we use different label.
Right.
So now we've seen, hey, we can find it with both methods. Now, ultimately, which method was simpler?
Cylindrical one.
Yeah, the Gauss Law one was simpler. It looks like a lot of work because I was explaining everything. But if you get down to it, you have to identify an appropriate Gaussian surface. You find the flux on that surface, and of course, the appropriate Gaussian surface is one to make it easy to find that flux. And then you calculate the charge enclosed, and then you just set them equal and solve. So it was a much easier method. So in a problem, like say it comes on a test, any problem in theory, if it's electrostatics, you find the electric field, you could use either one. Choose the one that's easiest. So if you have an exploitable symmetry, do Gauss's law.
Right.
If you don't, well, then you're stuck with Coulomb's law. And you know, I could do either one. So here is going through the steps, identifying, well, the electric field must be radial. The top view there made it easier to see the radial lines. And yeah, I didn't do the rest of the work on that slide. I left it to be done, which we've done. So now another question. We'll ask the entire class and see if you agree with the average. Which statement is true about the electric field inside of a conductor?
Electric field is 0.
Right. The electric field has to be 0 inside a conductor. That gives us some cool problems we can do. So here's a problem. A solid conducting sphere that carries a total charge of minus 16 microcoulombs, so that's Q1, is placed at the center of a hollow conducting spherical shell that has a total charge of plus 8 microcoulombs, so I'll call that Q2. The conductors are in electrostatic equilibrium, right? So there's that means there's no charge moving around.
Okay.
Determine the charge on the outer and inner surfaces of the shell and sketch a field diagram. Strategy, we can apply any of the conclusions we just reached about conductors in electrostatic equilibrium as well as the properties of electric field lines. But Gauss's law is our best solution.
Because there is spherical symmetry.
So I'm afraid I have the answers already written here. I do, but let's pretend that I don't have the answers and see how we get there. So first things first. Just to make life easy, I am going to start from the inside and work my way out. So this picture is only showing the inner sphere.
Right.
What's the charge in the inner sphere?
Wasn't it negative 16 microcoulombs?
Okay, I was just looking for Q1.
Oh,
It was either plus or minus. Yeah, it was minus 16. I'll write it up here.
Then Q2 was 8 microcoulombs.
Okay, so I have that Q1. Let's just make a Gaussian surface. Okay, that was a little off center. Not worth it. There's a non-perfect but closer to center surface.
Okay.
Okay, what do we say the electric field is inside the conductor?
0.
Okay, so how much flux is going through that?
None.
None. So how much charge is enclosed?
None.
Boom! How much charge is on the exterior surface of this thing then?
On the exterior surface?
That is on this right here. If that whole sphere has Q1 on it, and there's nothing on the inside, how much is on the surface?
On the surface, it should be negative 16 microcoulombs.
Right, all of it is on the surface. So we have 0 charge all the way through, and then when we get to the surface, boom, we have that minus 60 microcoulomb spread uniformly on this because of the symmetry.
Right.
And so if I go outside, if I make my Gaussian surface like this,
that's going to be minus 16 microcoulombs.
then the charge enclosed is my 60 microcoulombs, and my flux is going to be following all the things we've done. The electric field at whatever the radius r is here,
Right.
times 4 pi r squared, the area of that spherical shell, and that's equal to the charge enclosed, Q1 over epsilon 0. And so we get E is equal to Q1 over 4 pi epsilon 0 r squared.
And so that's going to be Q1K over R squared.
That's right. That's right. Now, let's look at the lines. What's happening to the space between the lines here compared to here?
Further out, they're slightly bigger.
What does that mean?
I don't know.
It means the electric field is getting weaker. The
Okay.
electric field strength is proportional to the separation of the lines.
Okay.
So you could look at the picture and say, well, it's dropping off with distance. The equation says it's 1 over r squared. And doing some geometry, you would figure that out even without the equation.
Right.
So now we've got the inside pretty much as fleshed out as we can get. Now we go to the bigger picture. So my Gaussian surface gets big enough to get to here. So let's make my Gaussian surface here. Okay, that's a perfect circle, as you can tell,
Indeed.
with some radius r that's between the inner and outer radii of that shell. what's the electric field on that Gaussian surface? Zero. So how much flux is going through it?
None.
So how much charge is enclosed?
None.
But we had minus 60 microcoulombs at the center.
Right.
So what's on the inside of the shell?
None. Oh, wait. Meaning what's inside that?
Remember, the charge can only, on a conductor, it can't have any charge distributed through the middle, as we showed why right here.
Right.
So this can have charge on the surface. So if this surface had is actually a negative amount, but if it had Q1 on it, how much is this surface going to have? The total enclosed is 0. What is this surface going to have to make it total charge enclosed is 0?
Should be positive 16.
Okay, positive 16 or minus Q1.
Minus. Yeah.
Right, since Q1 is negative 16, positive 16 is minus Q1.
So why do we have Q2?
Well, this shell has a total charge of plus 8. And we have plus 16 on the inside, so how much do we have to have on the outside?
Outside, we're going to have minus 8.
Which is minus 8. Right, you're doing the math, I'm doing it symbolically, but we're getting the same answers. So the external surface has Q2 plus Q1. So the inside sphere had on its surface Q1. Then the shell on its inside had minus Q1 to make so net enclosed was 0.
Right.
But then because we had a total of Q2 on that shell, the outer surface had to have Q2 plus Q1. And now if we make something like this, how much charge is enclosed by that?
And that it's going to be Q2 plus Q1.
Okay, so that means following all the same rules, we're going to have E
4 pi r squared. Q1 plus Q2 4 pi sigma epsilon 0 r.
and so there's the electric field we're going to have out there. You can see this is actually pretty quick, right? And in this case, we found the electric fields and we found the charge on each surface. We found both of those things by knowing how much total charge was on each object. So that's another good application of Gauss's law. Any question you have about this problem we did? I love this kind of stuff because it seems so hard, and yet it turned out to be so simple.
So simple.
Come on, a test, is it going to be hard or simple?
I sure hope it's simple.
Yeah, there we go. Okay, so we've done all the work on that. Now for problem, I think it's 6. No, it's 5. Problem 5. Problem 5 is the one that uses the differential form of Gauss's law. So everything we've seen so far was the integral form. It had an integral sign, right? And in fact, for the charge enclosed, you had to integrate as well. The differential form says that the gradient operator, that is the upside down triangle with a vector sign over it, dotted with the electric field, is equal to the charge density rho over epsilon 0. You can see a fair similarity between that and the integral form. Right, if I integrated both sides, the left side already has a d in it, right? Because the delta, well, yes, the gradient is derivative. And so we're in-gain derivative. Well, that makes sense. And we can see, well, that's going to give me something that has to do with electric field. And then on the right side, we have charge density over epsilon 0. We're going to have a dA we put. It's going to have to take a little work to get there, but you can see that it is relevant. And notice there I've written what the gradient operator is in Cartesian coordinates, because it's a lot easier in Cartesian coordinates than the others. And so here's the problem. The Earth's atmosphere in fair weather has been, if you're having an electrical storm, obviously it's different.
Obviously.
Experimentally, to have this functional form where E0, A, B, alpha, and beta are experimentally determined constants. I actually tried to look up what those were. I found a reference. Oh my goodness. Oh, I just have to slide this up. I found a reference there that has all kinds of information, but it didn't actually have numbers to go with this. So I put it there so you can look at it if you want. It's kind of fun. But what we want to do is we want to take this actual fitting equation for the Earth and calculate some things. So first, plot the electric field as a function of elevation. What are you going to do? What's it going to look like? First of all, positive or negative?
Positive. Oh. No, negative.
Negative. Now, what direction is Z pointing?
Up and down.
Okay, it's pointing out of the Earth. And so that means the electric field is pointing into the Earth. So let's start off right off the bat. If the electric field is pointing into the Earth, what kind of charge do we have on the Earth?
If it's pointing into the Earth, should be negative charge.
Negative charge. And now if Z goes to infinity, what is e to the minus infinity?
A crazy small number. 0.
Yeah, it approaches 0 as Z approaches infinity. So as you go infinitely far away, you're going to have the total charge enclosed is 0, which means that the charge of the atmosphere must be positive to counter the negative of the Earth.
Right.
So we can draw some conclusions. So you make this graph, and this graph for Z equals 0 is just going to be E0 times A plus B minus this pointing down. And then as Z gets bigger, it's going to drop down because of those exponents. This can look different, like if A is a positive number and B is a negative number, it can look different ways, but basically just draw an exponential decay, right? Don't try to over-trick yourself. Then describe how you plan to solve the problem. I plan on solving for this value by doing this calculation. Seems reasonable, right?
Yeah.
So which equation? I'm going to use differential form of Gauss's law. Set up and solve for the charge density. So here's where we have to do some math. So
Shouldn't that be beta?
yes, sir. Got carried away. Means you're paying attention though.
That was good.
First of all, the dot product. What does the dot product mean?
Multiplied parallel to.
Multiply the parallel parts. If we look at the red equation, the electric field equation, what direction is that in?
Yeah. No.
Well, x-way.
Z.
Z. So if we look at the blue, that has 3 directions. But 2 of them we don't care about.
Right. Because
there's no x and no y. So I am just going to, actually, let me just go ahead and add another slide. I was going to say, because I don't have another slide underneath this, let me just pretend, that's bad. I'm going to add 2 pages. Just give me plenty of room. I don't think I'm going to need it. So what I'm going to have then is this simplifies to del dot E is equal to d dz of minus E0 A e to the minus alpha z plus b e to the minus beta z. So I dropped off the unit vectors.
Where did your Z go?
That's what I just said. I dropped off the unit vectors because Z has a unit vector.
Oh, okay.
Because I was taking the Z component and the Z component. So now I have a scalar, because when you do a dot product, you get a scalar. There's no longer a vector. There's no x hat ddx because there is no x hat on the right-hand side. Next thing, what does that funny shape d mean?
Doesn't that mean like a partial derivative?
Partial derivative, which means that x and y are constants. Now, it turns out there's no x and y here, so there's no complicated factor.
Right.
But if there was an x and a y, we would not care.
Yep.
Because we're only taking with respect to z. And so now all I have to do is do this derivative. So So I brought down the derivative of the exponents. So I brought down minus alpha for the first one, minus beta for the second one. You will note I have a minus alpha right and minus in all the terms.
Yep.
So this simplifies to
Everything positive.
everything positive.
Plus beta beta z.
What do I do from there? I don't want to finish the problem. What do I do from there? And how do I do that? Yeah. So you can solve for rho simply enough. And I'm not going to write it here because I just want you to be able to do it yourself at the end. Now you have questions to answer about that. Sketch the charge density. So now you're going to sketch the charge density. Is it positive or negative? Well, what did we just find?
It was negative.
It was positive.
What?
Remember our negative times
yes.
negative?
The negative went away. Right.
Right, because the charge density in the atmosphere was positive. The Earth was negative, we determined because of the direction of the electric field lines. But if you get infinitely far away, you have zero and close, which means you have to have much positive in the atmosphere. And then, does it increase or decrease with z? Well, functionally, that's the same form as what you plotted the first time. If z is 0, then it's e to the alpha z's minus alpha z's are 1s. If z is infinite, e to the minus alpha z's are 0s. So it's going from a maximum value to 0. And then, is this expected y or y not? Well, I've talked to myself many times about why it's expected, so make sure you articulate that. Now, because we do have 13 minutes left, I can turn to the last two problems. The next to last problem, you have two spheres that overlap. So you have sphere 1, sphere 2, okay, that didn't overlap very well, but they overlap just a little. Obviously, for your problem, you want them to overlap more. And you're finding the electric field just in that region of overlap. Now, these spheres have a charge density doesn't matter which one you put as positive, which one you put as negative. Just make sure you make one positive and one negative. And you're supposed to find that electric field. So let's back up just one step. If I had just one sphere, how would you do it?
I have one sphere.
Yeah. Which is almost exactly what you had now.
Oh, I'd use a spherical symmetry thing.
And
Gauss Law.
Gauss's Law. Now we have two spheres. It broke the symmetry, right?
Yes.
But we can use superposition. Remember, when we were in class, general physics class, we said if you have multiple charges, you find the electric field from one, find the electric field from the other, and then what do you do?
Is it add or multiply them together?
Add them as vectors.
Add them as vectors.
So we have two objects that would be symmetrical. By the way, it's no charge in the region of overlap because one's positive rho, one's negative rho, so positive rho plus negative rho is 0.
Exactly. Yeah.
But we just treat each one as if it's complete. We calculate the electric field from each one and then we add them together. So what you need to do now is, well, something that I think is pretty obvious. I know I did a bad job of drawing, but make an axis that goes through both centers and then set the, let me change. Set your coordinate axis like this. So you have, this is 0, 0 there at the center of it. And so this is going to be x plus is this distance and x minus is this distance. X plus and x minus being something that has to do with how far they are from the overlap. Now I want to leave a little bit to you, so I'm not telling you what that is. And then
Why is your
there is a number given to you, by the way, that says that this distance here is d. So x plus x minus should equal d. Just, and the x plus and x minus are actually the same magnitude, the d over 2, it turns out, obviously. Then calculate the electric field magnitude as a function of radius. Now, keep in mind, you're only looking at the region of overlap, so you don't have to go outside of the sphere. Find it for each one. Break it into components. Break into x, y, and z components. And this is the last thing I'm going to tell you to help you on this one. Because this is three-dimensional, your E in the x direction is going to be your total E times x over r. And likewise, E in the y direction is E times y over r. And E in the z direction is E times z over r. Those are your directional cosines is what we call them. But it's if you know that, it makes life a little easier in doing it. So break them into x components, y components, and z components for each one, and then add them together. So I'm going to leave the mechanics of that to you. There's a good chance you'll come in and ask me questions, but I want you to try to think it through, especially since the last one you didn't get any chance to think. So that's a problem that you have to do. It turns out to be surprisingly really simple answer. The work getting there is not going to be surprisingly simple, but the answer is surprisingly very simple.
So we're asking about the field in
the field that I have
overlap.
Yeah, the field overlap. So okay, it's not erasing now, but I had it hatched as red. I'll just rehatch it.
No. I barely see it, but yeah, it's that.
Yeah, so we're looking for just the field in that region.
Wouldn't it just be 0?
It's not 0.
Interesting.
It's very simple, but it's not 0. Yes, by symmetry it's 0. Wrong. But last problem. The last problem requires, I put in 2 pages and I used them all.
Yes.
Put in a 3rd page. Okay, I'll do it.
Oh, I was kind of joking, but okay.
Yeah, well, what does it hurt to have a blank page at the end? The last problem is you have an infinite sheet with charge density rho, and we want to find the electric field. So everything in here has charge density rho. It's constant density, thank goodness.
Yes.
How are you going to find the electric field due to that charge?
I'm assuming we're going to use area.
Well,
Actually, hold on. It's a plane, and the charge is equal all the way through. It has planar symmetry, I'm assuming.
okay, the symmetry is the first thing. We're going to use whose law? Gauss's law with planar symmetry. And so, and the separation, I was looking at the problem definition there. I know I could have just gone to my version because I have it open.
Right.
But it says that it's 2D is the separation. So we have planar symmetry. What shape should we use for our Gaussian surface with this planar symmetry to take advantage of the symmetry?
A rectangle.
A rectangle works. I use a cylinder because the cylinder has less surfaces than a rectangle.
Well, let's use a cylinder.
Right, because everything you do is the same, it's just less surfaces to talk about. What was I going to say? I was going to ask you a question, forgot it. So let's move on.
Right.
We're going to use a Gaussian surface that's a cylinder. You have two choices to make on that cylinder. First of all, what orientation should I make the cylinder? What direction are the flat surfaces? Oh, I remember what it was. What direction do the electric field lines have to point based on this symmetry? Out, which means vertical. So the electric field lines must be going like this. And if it's a positive charge density, what direction are they pointing? In or out?
Out.
Okay, so the electric fields are pointing like this.
Yes.
So now with that, what orientation should we make our Gaussian surface?
Vertical.
Vertical is the correct answer. We want it vertical
Because we want it to be parallel with the electric field.
Where should it end?
Shouldn't it end below the plane?
That is one of the two options. Well, one option, I'll tell you the two options. One option is to end it right here in the middle. Because based on symmetry, if it's pointing out everywhere, it's got to be zero there. So that's one option. The other option is to be symmetric so that you have the same distance above and below. Either one is taking advantage of the symmetry.
Why don't we just do it all the way through? Because if you stop halfway, you're going to have to do two surfaces. This way you don't have to do one.
Well, if you stop halfway, the flux in the bottom is zero. Because the electric field has to be zero based on the symmetry. If it's pointing out, going up, above, and out, down below, in the midpoint, it has to be zero.
Okay.
So either way is just as easy. That's the important outcome. You just have to assign that symmetry and know what you're doing. Now we have two regions for our answer. This is one region. This is going to tell me the electric field outside of the sheet. But we also need to have one like this that will tell me the electric field inside. Okay, so we have our shape defined. We've defined what our symmetry is, what shape we're going to use, how it's going to be laid out. What do we have to do next? There's two things remaining.
Is it one of them define symmetry, or is that?
No, we've already
Okay, we covered that.
done that.
So then two things we need to do. Got to do the whole surface area thing.
Okay, we have to find the flux
Flux.
through the
yes.
surface. And what's the other one?
Find the charge.
Charge and close. Right, those are the two things. So one, flux through surface. Well, based on our symmetry, how much flux do I have on the side? Electric field is vertical. What direction is the dA on the side?
Zero. No.
dA is like that.
Yeah.
The electric field is perpendicular to that, so the flux is zero.
Oh yeah, it is zero.
So flux on the side, well, just side because I did a cylinder, so I have one side,
Right.
is zero because
DI is perpendicular to the D. Right.
okay, and then we have the flux on the top
Which is not zero.
Because on the top, the dA is going like that.
Parallel to it.
It's parallel, right? And the electric field has to be uniform. So it's going to be integral of E top dA equals, through all of the same steps we've done before, E top times the area of the top, which is pi r squared. What is r now?
R is the radius of the top.
R is the radius of our top, which is undefined. It better cancel out in the end or we messed up. All right? What about the flux in the bottom?
It's going to be the same thing. So instead of saying E top, it's going to be E bottom.
So it's the same thing. Because of symmetry, it's exactly the same
so
thing.
We could say that I bottom, if the flux in the bottom is equal to the flux in the top.
Yeah.
Go through all the steps.
Yes, yes.
Excellent. Less work is good.
So there that gives me the total flux is equal to 2 E top pi r squared.
That makes sense.
All right. Then what was job 2?
Find the charge. So the charge is going to be Q enclosed.
So A for Z less than D. And for B, we'll do Z greater than D. So Z is how far? Z is this distance here, right?
Right.
And so if Z is less than D, since we have a uniform charge density, the charge enclosed is just, well, what's charge density mean? Charge per
charge per area. No,
volume.
Volume.
So if it's charge per volume, how do I find charge enclosed? Charge density
Times epsilon.
times volume.
Volume.
Just
right. Because it's charge over. Volume.
Yeah. Rho is Q over V.
Right.
So Q is equal to rho V.
Yes.
So for this case, what is the volume?
The volume is 2D now.
We have a cylinder, so the base has an area of pi r squared. And then we have to multiply by the height, which is 2z because we did it symmetrical. Okay, what about this one here?
That one should be
Still pi r squared.
pi r squared times 2z.
2d because the charge stopped when z got to d.
Yes.
That's why it's different.
Okay.
So that's why we have part A and part B. Q enclosed is equal to rho times pi r squared times 2z. Q enclosed equals rho pi r squared 2d. What's the final thing we do mathematically? Really? I used up both pages. I wrote too big.
Don't we just add? No, we don't add them.
So we've calculated the flux, we've calculated the Q enclosed, we just put them in.
Right.
And so you're going to get two answers, one for inside of one for Z less than D and one for Z greater than D. And what you're going to find is one of them depends on Z and one's independent of Z.
Okay.
If you look back at your results for the cylinder, well, for a wire, for a point charge, okay, start there. Point charge electric field dropped off is 1 over r squared. We can tell that because the electric field lines were getting farther apart as you got away because they're going out radially. For the wire, it dropped off as 1 over r. The lines were still getting farther apart from each other, but only in 1 dimension instead of 2 dimensions. For this one here, the electric field lines are not getting wider or farther from each other. Hence, the electric field strength is constant once you're outside of that charged material, because the lines are not diverging or converging. And so it's not surprising when you think about what the electric field lines mean in this symmetry. Okay, I took over time. We started early, we ended late, but this was homework. Any questions before I turn off the recording?
Not right now.
Okay. We took essentially a full hour.